In the previous module, we just started with the scale analysis of mass and momentum equations. We got the scale of V as U infinity delta by L, and this was the scaling what we got from the X momentum equation. We were into Y momentum equation which we had written. So the scale of this term would be U infinity delta by L into 1 upon L into 1 upon L. So, comma, V is U infinity delta by L, del V, that is also U infinity delta by L into 1 by del Y, that is delta, is of the order of 1 by rho minus 1 by rho del P by del Y, I am keeping as it is, comma, nu V is U infinity delta by L into 1 upon L squared, comma, nu U infinity delta by L, because the scale of V is U infinity delta by L, and 1 by Y squared is 1 upon delta squared. Now, as I said in the last time, for the X momentum equation, L cube will be very huge term in the denominator as compared to here delta L. So, this can be neglected because delta is less than L. Delta is less than L. So, here what happens is both the terms are important, as you can see here, U infinity squared delta by L squared, U infinity squared delta by L squared is of the order of, both are the same, minus 1 by rho del P by del Y, comma, nu U infinity upon delta L. So, let us call this as equation 3. Now, we had kept del P by del Y, del P by del X as it is. Now, let us see what will happen. We know that pressure is a function of X and Y. So, we can write from partial derivative definition dP equal to del P by del X into dx plus del P by del Y into dy. Now, let me divide this by dx. So, I get dP by dx equal to del P by del X plus del P by del Y into dy by dx. Now, let me divide throughout by dP by dx. 1 equal to del P by del X upon dP by dx plus del P by del Y into dy by dx upon dP by dx. Let us just take only this term and see what happens to this. So, that is del P by del Y into dy by dx upon dP by dx is of the order of. Now, let us see here, just see this equation. Both the terms are important, means del P by del Y into 1 by rho should be scaling to nu U infinity by delta L. So, del P by del Y would be rho into nu, that means mu U infinity upon delta L. So, what would be the scale of dy by dx? Dy is delta, dx is L, because we have taken y and x as delta by L. What about dP by dx? Let us go to X momentum equation. If you see the X momentum equation, this is what we had gotten. So, here you see, if this term and this term are important, both should be of the same order. So, minus 1 by rho del P by del X should be of the order of nu U infinity by delta squared, but I want del P by del X. So, that means rho into nu means mu U infinity by delta squared, mu U infinity by delta squared. As you can see here, this is nothing but delta by L whole square. U infinity cancels out, and then you have U infinity, nu U infinity by mu U infinity into delta L, yeah, delta by L, yeah, L has come here, sorry, I was worried about L is there, L squared is there, sorry, mu U infinity by delta squared, it is there. So, but delta by L is very small. So, this delta by L is very small. So, whole of this term is to be neglected. That means what? This means that del P by del X equal to del P by del X equal to dP by dx, which implies that pressure is only a function of X. Pressure is only a function of X. That means if you come back to momentum equation, Y momentum equation, del P by del Y term is not there. If this is not there, I had taken both the terms are of the same order, then this is also not important. If RHS itself is not there, means then there is no LHS, so that means whole of it, Y momentum equation may be neglected. So what is that I am left out with? I am left out with X momentum equation. Now before I go to the X momentum equation, what happens to my flow over a flat plate? In a flow over a flat plate, if I take, see what is that I am doing here is, we have del U by del X plus del V by del Y equal to 0 and U del U by del X plus V del U by del Y equal to minus 1 by rho del P by del X plus nu del squared U by del Y squared. This is what we got from X momentum equation. If you recollect here, this term is not important, so this term is not important, so we have only nu del squared U by del Y squared. That's why I have written like that. Now I need to get this dP by dx term. What happens in a flow over a flat plate? We say we know dP by dx for flow over a flat plate is 0. Why? How do I understand that? Let's see that. We divide boundary layer and outside boundary layer. So this is viscid region and this is inviscid region. In the inviscid region, what is that we found? In the inviscid region, we know that U is equal to U infinity and V is equal to 0. And in the inviscid region, U infinity is constant for flow over a flat plate. How did I write this U infinity equal to constant? One way of looking at it is, if I put a pitot tube and measure pitot tube with the pitot tube, U infinity is observed to be constant. That's experimental. But if you take in the inviscid region, we define what is called stream function, U equal to del phi by del x, V equal to del phi by del y, and if you take your continuity equation, del U by del x plus del V by del y, if you write that, del squared phi by del x squared plus del squared phi by del y squared. If you solve this equation for this is what is called potential flows. From potential flow solution, if you solve for a flat plate, you are going to get U infinity equal to constant. Now you apply this to the Y momentum, X momentum equation in the inviscid region. So in the inviscid region, this boundary layer equation is going to become U infinity du infinity by dx. Why I wrote du infinity? Because U is not a function of Y and V is 0. V is 0, so this is 0 and you have equal to minus 1 by rho dP by dx, because we have just shown P is only a function of X and in the free stream it is P infinity plus nu into del squared by del y squared is 0, because nu is 0 in the inviscid region, nu is 0, U is equal to U infinity, V is 0. So, but I said U infinity is constant. So, du infinity by dx is equal to 0. So, implies dP infinity by dx equal to 0. Now, dP infinity by dx, how do I visualize that? dP infinity by dx is nothing but the pressure, this is nothing but the pressure impressed, this is the pressure impressed on the boundary layer. This is in the inviscid region, dP infinity by dx, it is pressing the boundary layer, it is pressing the boundary layer. So that is why dP infinity by dx would be equal to dP by dx, because that is the pressure which is acting in the boundary layer. Okay, So that's why dp infinity by dx is equal to dp by dx, but dp infinity by dx is 0. So dp by dx in the boundary layer is 0. So you have you get u del u by boundary layer equation is u del u by del x plus v del u by del y equal to nu del squared u by del y squared for flat plate. Now, what was the scale of this? This was on the left hand side, if you recollect, it was u infinity squared by L, and this was nu u infinity by delta squared. Okay, so what do I get? So I get delta squared implies delta squared by L is of the order of nu by u infinity, that is if I multiply in the denominator both sides by L, so I get nu by u infinity L, that means delta by L is of the order of REL to the power of minus half, where REL is equal to u infinity L by nu. So this is the boundary layer thickness. So we got part of our solution, that is delta by L. The story is not over because we need to get C of x. So C of x we know that is given by tau wall divided by half rho u infinity squared, and tau wall is mu del u by del y upon half rho u infinity squared. This is of the scales 2. Mu by rho is nu, and del u by del y is u infinity upon delta into rho is I have already observed in mu, and u infinity squared will be u infinity squared. So you get nu upon u infinity into 1 by delta. So C of x is of the order of nu upon u infinity. What is delta? L REL to the power of minus half. L REL to the power of minus half, that is nu upon u infinity L upon REL to the power of minus half, that is 1 upon REL into 1 upon REL to the power of minus half. So I get C of x is of the order of REL to the power of minus half. You see, from our non-dimensionalization we had gotten that delta is a function of Reynolds number and C of x is a function of Reynolds number. So we have gotten the same thing. What is missing now is only the constant. If you really derive that from similarity or integral approach, you are going to get this as 4.92 REL to the power of minus half, and C of x is equal to 0.664 REL to the power of minus half. So we, from the scale analysis, what is that we have found? Scale analysis, we have found that C of x decreases with the increase of the Reynolds number. And how does boundary layer increase with the length? If you just see this, you see, if you see this, delta is proportional to or is of the order of L to the power of half, because in REL L to the power of minus half is there, here L is there. So that is the reason whenever we draw a flat plate, we draw boundary layer growing, because delta is increasing with the increase of L. So we found from this flow over a flat plate, from mass and momentum equation, delta and C of x. Now let us start with energy equation. So we will do the scale analysis of energy equation. Let's do scale analysis of energy equation. Here to start off, because the boundary layer thicknesses are going to be different for Prandtl number less than 1 and Prandtl number greater than 1. So just back to slides, see Prandtl number is nu by alpha. So here for liquid metals it's very small, 0.004 to 0.03. For air and gases is 0.7 to 1, water is 1.7 to 13.7, organic fluids 5 to 50, oils it can be in the order of tens of thousands or 1 lakh, glycerin 2000 to 1 lakh. So if we get back to write up, so that is Prandtl number less than 1, which is liquid metal. This is liquid metal, that is sodium or mercury, implies nu is less than alpha, which implies that delta is less than delta t. I said nu means momentum diffusion. Momentum diffusion is going to decide delta. Alpha is going to decide delta t. So it can, alpha is greater than nu means for longer lengths this alpha can diffuse. That's why delta t is greater than delta. So if I draw that flat plate, you have delta and you have delta t. This is your U infinity, T infinity, and this is maintained at temperature Ts. Now let's try to draw the distributions of velocity and temperature within the boundary layer and outside it. So as the delta is very small, only within delta my velocity is, here it is U infinity, this is U infinity, and this thickness is going to be delta. Now here you have thermal boundary layer thickness is very large, so you have T infinity and this is Ts and this thickness is delta T, delta T. Okay, so now let us get back to energy equation. Let's get back to energy equation. U del T by del X plus V del T by del Y equal to alpha del square T by del X squared plus del square T by del Y squared. This is what we had gotten. Now to recollect, you see here delta is very small compared to delta T. Within the delta T, I can assume the velocity is U infinity because delta is very small, because U here, everywhere here I can take it as U infinity. So U is of the order of U infinity, V is of the order of U infinity delta by L, and T is of the order of Ts minus T infinity, that is I would call it as delta T. Okay, so if I substitute, and Y is of the order of delta T, thermal boundary layer thickness, because that's where the energy transfer is taking place. So if I put the scales or the orders of magnitudes of each term, so I get U as U infinity, del T as a delta T, and del X as L, comma, V is U infinity delta by L, and del T is a delta T, and del Y is delta T is of the order of alpha delta T upon X squared L squared, comma, alpha delta T upon delta T squared. Now you can see that delta T by L squared, again delta T by L will be very much less than 1. So this term I can neglect because of delta T by L is less than 1. So you see here, this term delta by delta T is very small, delta by delta T is very much less than 1. So the second term on the right hand side also can be neglected because delta by delta T is very, very small. So left hand side is U infinity del T by L is of the order of right hand side alpha del T by delta T by delta T squared. So delta T cancels out. So I get delta T squared upon L is of the order of alpha by U infinity, which implies delta T by L whole squared, that is I am multiplying in the denominator by L, that is I get nu by U infinity L into alpha by nu. What did I do? I multiplied by L in the denominator both sides and multiplied and divided by nu in the numerator and denominator. As you can recollect, this is nothing but 1 by REL, and nu by alpha is Prandtl number, so this is going to be 1 by Prandtl number. So that means I get delta T by L is of the order of REL to the power of minus half PR to the power of minus half. You see, if you recollect, when we said that when we non-dimensionalize the energy equation, we said that it is a function of RE and PR, we are getting RE and PR only. RE and PR only. Now let us take up Nusselt number. So Nusselt number is equal to HL by KF. But what is H? H is equal to minus K del T by del Y upon Ts minus T infinity into L upon KF. So that is K, KF gets cancelled out. So you have del T as of the order of delta T upon Ts minus T infinity into delta Y is of the order of del T, and you have L. So you get this is of the order of L by delta T, that is Nusselt number is of the order of delta T by L to the power of minus 1. If you recollect, we just now found delta T by L as REL to the power of minus half PR to the power of minus half. So I get Nu is of the order of REL to the power of half PR to the power of half. So you have delta T by L of the order of REL to the power of minus half PR to the power of minus half. Nu is of the order of REL to the power of half PR to the power of half. Okay. So this is, so what do we understand from this? Again here delta T is of the order of L to the power of half. So that's why thermal boundary layer thickness increases with the increase of length, and Nusselt number increases with the increase of Reynolds number, and Nusselt number increases with the increase of the Prandtl number. Remember, we have derived this only for Prandtl numbers less than 1. That means delta is less than delta T. Okay. So next is, in the next case, what we are supposed to do is we are supposed to take up Prandtl number greater than 1. That is what we call as thin thermal boundary layer. Thin thermal boundary layer. Thin thermal boundary layer. Okay. So in this thin thermal boundary layer, Prandtl number is greater than 1. So you have nu greater than alpha. So which implies that delta is greater than delta T. Because nu is greater, so for longer distances momentum can diffuse, because of which delta is greater than delta T. So now let us take up the drawing. So if I take the flat plate, so this is my delta T and this is my delta. This is my delta. Now if I were to plot the temperature, this is of course you have U infinity and T infinity flowing. So now you have the velocity distribution varying, delta is large, so your velocity is varying like this, U infinity. So this thickness is my hydrodynamic boundary layer thickness delta. Okay. So now you have thermal boundary layer thickness very small, so you have this is T infinity and this is my Ts and this is my boundary layer thickness delta T, thermal boundary layer thickness. As you can see, delta is greater than delta T. See here a tricky situation. Earlier in my case, here it was, what was the case when Prandtl number was less than 1? I could take within the thermal boundary layer U equal to U infinity. Here I can't do that because my thermal boundary layer thickness is very small and U is no longer U infinity, it is varying. Here what I am doing is, because the delta is very small, I have assumed that the velocity distribution is linear. within the thermal boundary layer. That means u is equal to my plus c. This is x direction, this is y direction. So when y equal to 0, u equal to 0, that is no slip condition. So you have c equal to 0. This implies it is c equal to 0. Now when y is equal to delta, u is equal to u infinity, correct? So outside the hydrodynamic boundary layer thickness, my velocity is u infinity. I get u infinity equal to m delta. So m equal to u infinity by delta. So now at y equal to delta t, because that's where I want everything happening. So u equal to m is u infinity by delta, y is delta t, c is anyway 0. So this is my velocity u. This is my velocity u. Okay. So now if you take continuity equation, del u by del x plus del v by del y del v by del y equal to 0. Del u by del x plus del v by del y equal to 0. So you have scale of u is u infinity delta t by delta into 1 upon x is L, and v is what I am looking for, and y is delta t. So v scales down to u infinity delta t squared upon delta L. Let's keep it like that. Now let us get back to our energy equation. In my energy equation, I get u del t by del x plus v del t by del y is equal to alpha del square t by del x squared plus del square t by del y squared. So what is the scale of u? It is u infinity delta t by delta into delta t by L, x scales to L, comma, v is u infinity delta t squared upon delta L into delta t upon delta t is of the order of alpha delta t upon L squared, comma, alpha delta t by delta t squared. You see here both the scales are same, and this scale is very small, this can be neglected. So we end up getting u infinity delta t by delta L is of the order of alpha by delta t squared. So delta t cube by L is of the order of alpha by u infinity into u infinity. So this implies that delta t cube by L cube is of the order of nu by u infinity L into delta is missing. So here I have missed out delta. So you have delta here. So you have nu u infinity L into alpha. This is actually, I need to write this as L, alpha by nu into delta by L. What have I done? I have multiplied by L squared on both sides, and that 1 L I have taken here, 1 L I have taken, multiplied and divided it by nu. In the next module, we will do the simplification and get to the delta t by L cube. Thank you.